No.
Good afternoon, everyone. Thank you so much for being here. We're very glad to welcome you to this sixth edition of our wonderful and great Gaza Excellence Talks. We are extremely pleased today to welcome our first Nobel Prize, Dr. Michel Mayer. Um, and we are very pleased to have this session at a time when things are getting worse in Gaza and getting worse for Gazan students, for Gazan colleagues, and for Gazan universities in what is now quite universally accepted to be a genocide, in effect. And when, as you probably most of you know, the flotilla has been arrested. So it's a particularly important time to show our support and solidarity for education in Gaza, for Palestine in general, for universities and colleagues in Gaza, and to show that science is universal, to show that we are here with you in Gaza, for all of you in Gaza and in Palestine in general, and we will be steadfast as you are, and we will be resilient as you are, and we will stay with you as long as it takes, forever. I will now, unfortunately, as you know, these talks are co-organized by our organization, Academic Solidarity with Palestine, and the University of Al-Aqsa in Gaza. Unfortunately, they don't seem to have been able to connect right now, given the internet problems. However, our head of operations in Palestine, Dr. Saida, is here and will say a few words on behalf of Palestinian scholars and Palestinian universities. Then I will briefly introduce Michel Mayer as if he needed any introduction, and then the floor will be his. So over to you briefly, Saida.
Thank you, Christina. Good afternoon for everybody. On behalf of our colleagues at Al-Aqsa University and all Palestinian University, we are honored to conduct this webinar and to have Professor Michel Mayer and listen to his talk. We appreciate all your solidarity and support, and without this solidarity, we will not be able to continue to resist and fight for our right for education and for peace. Through your solidarity, we will keep hope and we will continue to learn and to learn together how to keep existing on this global despite of all the odds. Thank you very much for being here, and I hope that next time our people from Gaza will be with us. They are with us with their spirit and with their solidarity. Thank you.
Thank you so much, my dear Saida. Let's now introduce our Nobel Laureate and wonderful speaker of the day, Dr. Michel Mayer, who will be telling us about other worlds in the cosmos. For those of you who don't know him, which I doubt not many, we can't be talking about many of you because he's so well known. Professor Michel Mayer is an emeritus professor at the University of Geneva, and he was awarded the Nobel Prize for Physics in 2019 as being the first person, together with his student Didier Queloz, to find a planet orbiting a sun-like star outside of our solar system. Until recently, the solar system has provided us with the only basis for our knowledge of planets and life in the universe. In 1995, Professors Mayer and Queloz have dramatically changed this view with the discovery of the first giant planet outside the solar system. This seminal discovery and the development of new astronomical equipment and observational approaches has spawned a revolution in astronomy, both in terms of new instrumentation and understanding of planet formation and evolution, and ever more than 2 decades after this discovery, thousands of extrasolar planets have become known. In the future, Professor Mayer research is expected to bring the discovery of a second Earth, a habitable with the potential to support life, to the fore. And thank you so much, Michel, for being with us. Your support is invaluable. And I will now, the floor is now yours. Thank you very much.
Thank you very much for the invitation to speak to you. I will just say a few words before starting discussing my own topics. Dear friends of Gaza, in Gaza, dear friends of science, science is universal. It belongs to everyone. I am sure that you share this belief. In this day and age, when facts are too often overshadowed by so-called alternative truths, I take great pleasure in discussing science with you. Aware of the current scandalous situation in Gaza, I feel the need to maintain this contact with you, my colleagues. Voilà. So now speak about my own topic. It's a very important time for me because it's almost exactly 30 years ago we did the announcement of the discovery of the first exoplanet. It was the 6th of October 95. And from the time, the quantity of new results is absolutely exceptional. So I would like to discuss what was learned on the last 30 years and the prospect for the next big question, do we have the possibility today maybe detect life in the universe? So it's very impressive for me to realize that already more than 2,000 years ago, Greek philosophers was already discussing this question. And for example, we have a very famous letter from Epicurus, 3rd century before Christus. And so he said in this very long letter, words are in an infinite number, some of them similar to our own one, some others being different. And later, in the same letter, he did this very interesting statement that living species, plants, and all the other visible things could exist in some worlds and could not be in others. It was not a problem of exoplanet. It was more philosophical view of these other worlds. And continuously on the last 2,000 years, theologian, philosopher first discuss these questions, and then more recently, evidently, scientists. What was the general feeling of the population of people? And for example, you have this Giordano Bruno in the 16th century made the proposal that it was not a scientist, that the sun is a star. It's only brighter because it's closer. We have planet orbiting the sun. So he said we can expect the other stars should have planets. And this was a change from a philosophical meaning as a words to something more specific, exoplanet. And you can see here a copy of atlas from the made in 1742, so already a long time ago. And okay, you have the impressive solar system in the middle with the sun and so on, the planet. But if you are looking in the upper right corner, you can see that you have distant star. And if you zoom on this, you can see that already at the time, they illustrate this distant star by some of them with surrounded by a planetary system. So you see, it was quite common in the time to, yes, we have some planetary system in other parts of the universe. So if we move to a modern view of this question, okay, as you know, we are living in a galaxy, the Milky Way galaxy, with something like 200 billion of stars. And evidently, the immediate modern question we can ask is how many Earth twin or how many planets, planetary system we have among part of this all these stars. So if we have a modern picture image of a very teeny part of the Milky Way, you can see the huge number of stars. Stars are similar to the sun. So you see all these small dots are equivalent to the sun. And the question we can ask immediately, how many planetary systems are hosted by these different stars? Now, it's very strange to consider what was the believing of astronomers during the 20th century. In fact, it's completely crazy to see exactly at the opposite of the public meaning. Astronomers do not believe that we have other planetary systems in the Milky Way. Here you have a graph. It's a logarithmic scale on the ordinate, and you see that before the middle of the 20th century, people consider the big name of astronomy, consider that we are alone in the Milky Way. Completely crazy. 200 billion stars, and we are alone as a planetary system. And evidently, this was based on a very erroneous theory that because to form planet orbiting a disk, all of them in the same direction, already from Laplace and Kant, it was hypothesis that, oh, sorry, j'ai des perturbations.
T'inquiète, prends ton temps.
No, so to form the planet, we need to have a disk of dust and gas, and it's only the. Oh, sorry, I have to suppress these stupid things. Okay, sorry. To form what are the different possibilities to form a disk of dust and gas? In fact, it was believed that the only way to do it was to have a close interaction of two stars, and the close interaction was by tidal interaction will induce the formation of a disk. But if you do the calculation, 200 billion stars during 10 billion years, and you have no situation like this. This is a good example of the vacuum existing in the Milky Way. We are mostly at so big distance from star to star that we do not have any close encounter. So this is not working. And this was the reason why the expectation was to be alone in the Milky Way. And in the middle of the century, suddenly people realize that we have new stars formed by collapse of disk of big clouds of dust and gas, and in the collapse of this strong turbulent gas cloud will be induce an excess of angular momentum during the collapse, and this excess will create a disk of fast rotating matter around the young stars. And immediately, the ideas change on this matter. If it is really related to the excess of angular momentum during the collapse, we should have planetary system surrounded, hosted by any new stars. So immediately the estimation of the number of planetary systems in the Milky Way jumped to 10 billion, 100 billion of systems. Every star should have planets. And you see, and this is absolutely confirmed by modern detection measurements. And this is was the first to have discussed this question was Otto Struve. It's not a paper; it's a letter of 2 pages published in 1952, and he was measuring the velocity, the rotational velocity of solar-type stars, and he discovered that all these stars were very slow rotators. So you see, if they are slow rotators, where is the angular excess of angular momentum? And he realized this is the origin of the formation of this disk of dust and gas. And he finished this abstract. Therefore, there can be many planet-like objects in the galaxy. So it's a change completely of paradigm in the middle of the century. If we have a look on a galaxy similar to the Milky Way, but seen on a different angle, you see that along the spiral structure, the spectral arm, you can see that you have a lot of pink cloud, and this is the region where you have the formation of a new generation of stars and planets. And for example, maybe you have already seen this very famous molecular clouds. It's the Orion Nebula, very well measured, not too far from the solar system. So, and 30 years ago, the Hubble Space Telescope made some measurement with a high resolution characteristic of this instrument. You can see that you have in face of the nebula, you have some small stars, and these are young stars just going out of the nebula. And looking with a good resolution of the space telescope, you can see all of them are surrounded by a small disk of dust and gas, as expected by Struve. And evidently they appear in black because they are stopping the light coming from the nebula. And this was the direct images of the place where we can dream of the formation of new planetary system. And if I go back to the same image, here, okay, you have, I don't know how many stars on this image. We can detect planet orbiting these stars. And we have already to remember that the luminosity is coming from the stars, nuclear reactors, and the planets are only reflecting a small fraction of the luminosity received from the star. So just as an example, if you look the solar system from some distance, in fact, Jupiter, the big planet of the solar system, reflects something like billions of the luminosity of the star, so of the sun. So at some distance, you are completely dominated by the luminosity of the sun, and you cannot see the planets. So the detection of planet by direct imagery is not simple at all. So 35 years ago or something like this, having developed a new instrument with some of our French colleagues, we have made a different approach. So if you can see the small drawing on the left, that you have a planet orbiting the star. You cannot see the planet, but the star itself is slightly moving around the gravity center. And if you measure the velocity by the Doppler effect, in fact, you can measure the orbit, projected orbit, due to the motion of the star and not the planet. After, you can easily do some calculation to detect to measure the period, the shape of the orbit, estimation of the mass, and things like this. And what the advantage of this technique that you have in the spectra spectrum of the star, you have a huge forest of atomic transition. And this huge forest you can see on the below of the slide. Uh, uh, all the trick is to try to measure the very small Doppler motion of this forest of atomic transition. So you don't have so many photons coming from stars. So what we did is try to build an instrument doing some kind of correlation to contract all the Doppler information in the spectra to one single quantity, the velocity. And this is the way we achieve high precision. And we start, I ask the committee of program of the 2-meter telescope in Haute-Provence in south of France to try to search for planets with this new instrument. It was considered to be a huge program at the time. It was something like 42 nights, observing nights per year. And we have selected a sample of stars similar to the Sun. And we were expecting to detect first what kind of very small star called brown dwarfs, stars not producing any nuclear reaction. And only after maybe 10 years, we are dreaming to detect planets, because the theory said that giant planets like Jupiter and others, to be formed, to be created, need to agglomerate ice particles. And ice particles do not exist close to the star. So the theory at the time was to form planets like Jupiter, Saturn, and others. The orbit should be at least 10 years or more. And this was a big surprise of what we did, because the first object we have discovered first was an object with a period of 4.2 days. So was this in a disagreement with the theory of 1,000. So, okay, when you have a discrepancy of so big, you have to be a little bit careful. And so it's the reason why we have decided to repeat the measurement 1 year later to eliminate other possibility of change of velocity, for example, related with the magnetic activity in the atmosphere of the star, or rotation of a star and things like this. And it is, but this object was really, really impressive. This is so unusual. And evidently, what was the theory? What was the people discussing this question? And it's very, very interesting that to see that already 15 years before, Goldreich and Trement, the big name of astronomy, and then after Papaloid, Zulin, and others, analyze the problem of if you have an embedded body in a disk of dust and gas, what was the result? And they discover that it's a simulation here. Here you have the very small young object form, and immediately the gravity induced by the planet will induce at the position of resonance in the disk an excess of matter. And you have, after the reaction of all this resonance to the orbit of the star itself, of the planet itself, and the net result, it's a little bit complicated calculation, is the migration of the planet from some distance, very large distance to the star, to be closer to the star, spiraling. And this was the proposed explanation why we have so short period observed. And this is a very major ingredient of all theory of the formation up to now, to introduce in the theory of the formation of planetary system this problem of the migration of young formed planets. So having discovered this first object in the northern sky, we have decided to build new instrument, more ambitious, vacuum with extreme thermalization, higher resolution, and so on, to be mounted on a 3.6-meter telescope in Chile, on the observatory belonging to the European Association of Astronomers in the Southern Sky. It was this instrument was implemented on a big 3.6-meter telescope, and with all the trick to have a much better resolution and stability. And we start a huge program in the southern sky, and we discovered a huge number of planets. So just to illustrate a little bit how it works, okay, you choose one target and you measure the velocity. And here you can see small red symbols versus the day where we have made the observations. And you see year after year, month after month, we have measured the same star with changing velocities. And after, I don't know, several years, 8 years, you have all these different measurements, and it's easy after with the computer to see this is the global result of 3 different planets. And for example, here it's not periodic, but it's periodic with 3 different planets, with and this is correspond to 3 planets or something 10 times the mass of the Earth orbiting the star. This was the first system like complicated like this discovered at La Silla. So after 30 years, okay, having developed this new instrument, powerful instrument for La Silla observatory, we have been granted by the committee of this observatory a huge amount of 500 nights on this 3.6-meter telescope to do a systematic survey of the southern sky. And the discovery was made, the first discovery made was, you see that here you have different techniques. The red symbols correspond to the discoveries of made with the Doppler techniques. So the diagram is a mass logarithmic scale versus the distance between the planet and the star. And you see first, okay, one Earth, one mass Earth, and one astronomical unit will be it's a blue symbol here. But you see, all the exoplanets discovered completely covered the plane between mass and direct imaging. So at the opposite of what we have in the solar system, you have Jupiter-type planet at very short period, like we have discovered the first one, but you see very low mass planet with a mass about the mass of the Earth, with distance or with period correspond to few hours. You have some planet extremely close to the star, and evidently we do not have anything similar to the solar system. The second point we can notice that, for example, the red symbols, you have a huge excess between 1 and 10 times the mass of the Earth. But in the solar system, we do not have such kind of population. So this is typical of what was discovered during the last 30 years. This amazing diversity of planetary system. The solar system is certainly not a unique example of what we have in the universe. And you see that you have different colors. And for example, the first tool used to discover planet was the Doppler spectroscopy. But then after, you have the emerging of this green symbol, blue symbol, And this is correspond to the planetary transit technique. I will describe this later. And you have also few of them in green. This is direct imagery. No, this is gravitational bending discovered by the different technique. And the direct imagery is the point in the upper right corner. And here I will show a few slides on a new instrument installed something like 10 or 15 years ago on an altiplano of Chile. Oh, sorry, it's in French. It's something like 60 dishes of 12 meters, and it's an interferometer, so you can combine the signal received from the different antenna, and with a huge resolution, because the spacing of the different antenna could be as large as 14 kilometers. So you have an absolutely fantastic resolution, and mostly you are sensitive to wavelengths sub-millimeter, so you can study the formation of galaxies, planets, and interstellar matter. So this instrument was built in common between all the countries of European countries, the US, a few American university, and Japan. Okay, this is just to see that it's a nice place. It says 5,000 meters of altitude, and this is a normal picture of the sky, photography, and you can notice a very small cloud is much smaller than Orion Nebula, and this small cloud was known to have one or two young stars formed recently. And some colleagues observing with this instrument observe this cloud with this interferometer, and this was the result of the observation. So you see that with a high resolution possible with this interferometer, you see that you have a disk of dust and gas surrounding the young star, but with this kind of torus of missing matter, because this is all the matter in this dark ring was used to form new planets. So this is a direct image of a new planetary system in formation. And evidently, you have the possibility to do some physics of this kind of disk. So it's very stimulating. And so these people was very encouraged to measure other young stars. And you see here a set of new young stars, all surrounded by disk of dust and gas, and with the characteristic of the formation of a new planetary system. If I go back to my own domain of Doppler spectroscopy, this is an image of the top of the Paranal Observatory, also in the north of Chile, in the Atacama Desert. It's something like 2,400 meters of altitude, so it's not extreme altitude, but it's very desertic. In the far, you can see the cloud about the ocean, Pacific Ocean, and in this observatory, you have 4 big telescopes, each one with 8 meters of diameter. And underground, you have a lot of possibility to do instrumentation and connect to this different instrument. And at the Geneva Observatory, one of my young colleagues takes the lead to develop with many other institutes to develop a new spectrograph with a cab underground to be with the possibility to be connected to one 8-meter telescope or to the four 8-meter telescope, so something equivalent to the size of a unique 16-meter telescope, so to have a huge number of photons, because to measure the very small Doppler shift due to a small planet, rocky planet, we need a lot of photons. Why? Because the Earth induce a change of the velocity of the sun only at the level of 10 centimeters per second. So we are dreaming to measure, and we achieve it, to measure the change of the velocity of stars at the level of few centimeters per second. Or just to have, this is the forest of atomic transition. It's only 1/10 of the domain used on the last instrument. So it's a huge forest, thousands of atomic transition. And the instrument was supposed to measure the small wobble of this forest of line. And just to have an idea of the challenge to detect rocky planets like the Earth, so you need to measure Doppler shift 1,000 times smaller of the width of the atomic line. So the narrowest line here are 1,000 times bigger than what we are dreaming to measure. This is just the techniques to see. It's not completely easy. And just one example observed with this object, it's the closest star of the solar system, Proxima Centaurus, and this is something like four light years from here. And you see that two measurements made by these two instruments we have developed, HARPS and Espresso, and you see that we have detected already two planets. Maybe a third one is appearing. And for example, just notice the Proxima D is a name for this planet. This is correspond to an amplitude of the change of the velocity of 38 centimeters per second, and this corresponds to a mass of the quarter of the Earth. So just to explain the progress in instrumentation. And this is, for me, it's very impressive to see the progress we have made during the last 50 years. For example, my first spectrometer was made, Coravel was made in 1977. It was on a 1-meter telescope, and the precision was 300 meters per second. So it was very nice for studies like stars motion, but not for planet. LOD, the spectrograph used to discover the first planet, the precision 94 was 13 meters per second. And the last one, Espresso, arriving at 0.1 meter per second, was developed and put in operation in 2018. So you see, it's a factor 3,000 in a little bit more than one generation. And the story is not finished. Here, after 4 years after the discovery of the first planet, we discovered many others, but one with a period of only 3.5 days. So a little bit closer to the star itself. And as we did many times before, we try to see if by chance we have a transit. What is a transit? It's simply the fact that the planet crosses the disk of the star and create a small eclipse, a small diminishing, a small dip of the luminosity of the star. And exactly at the time predicted from the Doppler spectroscopy, we've seen this small drop of the luminosity. Here it's a little bit less than 2%. So evidently, if you have the relative size of the star and the planet to the star by this kind of techniques. The Doppler spectroscopy gives you access to the mass. So if you have the mass of a sphere and the size, you can easily determine the mean density, and the mean density of this object is 1/3 correspond to 0.3 gram by cubic centimeter. So this was a direct proof of I will voilà. This was a direct proof of the gaseous nature of this object. It was not believed by any astronomer still at the time. But 1 year after, and one small anecdote, you see, I was collaborating with colleagues in US, and the measurement was made with a 10-centimeter telescope in a garage. It was not big telescope to having made this measurement. But 1 year later, this colleague repeats the measurement with the Hubble Space Telescope, 2.4-meter telescope in orbit, and you see when you are above the atmosphere, the quality of the signal you can have. And immediately to say, oh, if we have such a high quality, it will be possible to detect other much, much smaller massive planets. And this was made first by a small French telescope, but then after the NASA Kepler space mission made absolutely an incredible harvest of new discoveries. The idea is very simple. Okay, the realization is complex, but the idea is very simple. This telescope, it's about 1 meter size of telescope in space, and it was measuring a small part of the sky where you have some more than 100,000 stars. And they made one measurement after, let's say, half an hour. And they continue to do it continuously during several years. And what you have at the end, it's, let's say, 100,000 luminosity curve. And when you analyze this with the computer, you see that you have a huge number of planetary systems. Many, many of stars sometimes have the crossing of the disk due a transit by a planet. And here you have a plot by the Kepler consortium, and you have the logarithmic scale with the radius compared to the Earth's radius on the ordinate, and you have the period of the object detected. And the black dots correspond to stars with only one transit, periodic transit, let's say every day, or every 10 days, or every 100 days, etc. You have the repetition of the transit. But you see that you have a lot of symbols with colors. And for example, if you look only the red colors, this corresponds to stars with 6 planets orbiting, transiting in front of the disk of the star. So and other colors correspond to 4, 5, and so on. So you imagine that you have a huge number of planetary systems in the Milky Way. And this confirms fully that probably all stars in the Milky Way have planetary system. Going back to a small cartoon, to this technique of transiting planet. Okay, you have the big yellow disk correspond to the star. The dark black symbol corresponds to the planet orbiting, crossing the disk. When the planet is in front of the star, you can measure the size of the planet. But when the planet go below the red part here, when the planet is behind this, you have a small dip of the luminosity in the infrared. And this drop of infrared luminosity allows the measurement of the temperature of the atmosphere of the planet. But what is the most important feature of this disk is this small blue ring of this planet when the planet is in front of the star. And this corresponds to the atmosphere of the planet. And evidently, this atmosphere will filter a little bit the luminosity coming from the star. So if you compare at the end the spectra of the star when the planet is in front or when the planet is behind, you have access to the effect of the field of the atmosphere. And you can start to do chemistry of the atmosphere of the planet. And this will be the tool used in the coming years to search for what is called biomarkers, study, let's say, molecules related to the chemistry of life. And this is absolutely very active domain. And the idea is to see if we have the capability to detect life on some of these planets. In fact, the big question behind is life a cosmic imperative? Let's say when all the condition, chemical, temperature, and so on, conditions are realized, do we have some belief that life will emerge by a set of very complex chemical reaction and situation? This was a proposal made by many scientists in the past to have the possibility to answer this question. Just to realize the difficulty of this kind of technique, here is a real image of the sun with all the magnetic activity in the atmosphere, and you have a small box on the in the right, upper right. And in the middle of the box, you have a small blue dot. This is the Earth at the same scale. So let's imagine you have two possibilities. First, to see the change of the velocity of the big sun due to the small Earth mass, or to see the drop of the luminosity when the planet crosses the disk. Just to have an idea, it's not easy. And evidently, the atmosphere of Earth-type planet are rather fine. It's not very impressive. It's very small. So the change of the spectra due to the transit of the planet in front or behind, in fact, it's very, very small. You need a huge number of photons to see the effect of the filter of the Earth-type atmosphere. And what are the expectation we can have? Here, this is a project at the present time developed in the Atacama Desert on another mountain at 2,800 meters of altitude. And this, what is absolutely impressive, that this project is a telescope of 39 meters of diameter. It's not a single dish. It's, in fact, it's a combination of a huge number of mirror of hexagon mirror with an optical quality to have a very perfect image. Just have an idea of, it's so impressive. You have two cars in front of the telescope here. You see, it's a huge, huge, huge. So in 2023, this was the situation of the construction. This is the dome. The telescope is still not there here. And here you have the same last year, the same situation of the construction. The first part of the telescope can be seen in the opening of the dome here. And maybe to have an appreciation of the sky, you have a small car on the left, one red and one blue and one white. And this is absolutely fantastic. This will be by far the largest telescope ever built. This is a cartoon, an artistic view of this new telescope, where you have all this laser, and you are using the retrodiffusion of the atmosphere. We are doing some small correction at 1 kilohertz of all the turbulence affecting the atmosphere of the Earth's atmosphere to have absolutely perfect images not affected by the turbulence of the atmosphere. So maybe you can recognize this planet. It's a rocky planet with just a small quantity of water on top. You see 3 kilometers maybe of ocean compared to 12,000 kilometers. It's really a it's a wet rocky planet. So, but these are the very important type of planet for the development of life. We are, with the Doppler technique or transit, we are detecting a rocky planet. So maybe still not with a good condition, but we detect planet. And I will finish with just showing first result coming from the new space telescope called James Webb Space Telescope. At the present time, just to have an idea, 1/3 of this telescope time is only devoted to extrasolar planets. It's working in the infrared. This is the reason why it is coated with gold. And you can notice the same diagram we have already seen before. You have the Earth, the mass of the planet discovered up to now, logarithmic scale versus the period of the different objects. And you have different colors coming also again by the different technique used for the detections. And it was not completely adapted. It was what we have in 2021. So this region corresponds to almost normal Jupiter like we have in the solar system. After here, you have this kind of Jupiter close to the stars, very hot, like we have discovered with the first 151 peg. Here you have a lot of Neptune-type planet, but the Neptune in the solar system corresponds to the green symbol very far from the sun. But here you can see in the universe, you have a huge number of Neptune-type planets at any distance, very close to the star. So it's completely new. And then after you have the rocky planet with a very small mass from the Earth's mass or below. So the telescope will study all these kind of objects, but for the present time, with some special focus on what is called temperate rocky planet, because due to instrumental technique, we have some difficulties to detect long period low mass planet. So it's the missing part in this diagram to the right and below is only due to the bias from the instrument. So for the moment, people try to study mostly what is called temperate rocky planets. And again, we can see this simulation with not simulation, it's a cartoon, we correspond to what is called the transmission spectroscopy. So the comparison of the star when the spectrum of the star when it is affected by the planet in front or behind, And so when you compare, you have the possibility to start to do chemistry of the planetary atmosphere. No, what is it? This is a crucial point. If the wavelengths where you are measuring is stopped at very high altitude in the atmosphere, the planet will appear relatively large. If, at the opposite, if the wavelengths you are measuring is going down very deep in the atmosphere, the planet will appear very small. So just you have a very good example in the Earth's atmosphere. If you measure the size of the Earth from some distance, in the yellow, you will have the classical diameter of the Earth. But if you do the same measurement in the 9.7 micron in the infrared, in fact, you will be the luminosity, the wavelengths, will be stopped at 40 kilometers from the ground because this is correspond to the ozone absorption. So you see that you have a link between the contrast of the deep of the transit and the opacity in the atmosphere. You see that you have different depths coming from the different luminosity we have measured. And it's incredible. It's so simple because simply the contrast of the deep of the transit is help you to do direct chemical analysis of the composition. You don't need to build new instrument. Eventually, you need a lot of photons to do this kind of measurement. And this is real measurement made from, okay, the name of the planet is not important. It's called WASP-39, made by the James Webb Telescope at different wavelengths. And you see that you have small difference from one to one different colors or wavelengths. And if you analyze carefully this difference, is what was made already 3 years ago. You see, take notice, it's simply the transit depths here. It's nothing complex. It's directly the depths of the transit, 2.1%, 2.2, and so on, 2.3. And okay, you have changes of the depth at the level of 1,000. And if you plot this change of the depth as a function of the wavelengths, you can see you have dramatic change. And for example, this huge feature at 4 and something micron correspond to the carbon dioxide, and so on and so on. So here you have a good example of the future. So you do the chemical analysis of the atmosphere of planet simply by using these kind of tools. And eventually you are dreaming to look what is called biomarker, so set of different kind of molecules related with the chemical of the chemistry of life. Okay, the methane was not discovered during this study. And if we are looking on the future, you can see here always a plot of the diversity of planetary system, the logarithmic of the mass, the logarithmic scale of the semi-major axis of the orbit. You have different colors for the different techniques used. We have the huge triangle where we do not have any detection due to the limitation of the instrumentation. But one satellite was launched a few years ago called the Gaia satellite. It's an interferometer in the atmosphere and measuring million of stars and to see the position. So in the domain of exoplanet, this satellite will see small change of the position of stars due to the motion around the gravity center of some planetary system. And in probably 1.5, 2 years, they will announce, I'm sure, thousands of new planets, mostly in the region of the domain called detectable Gaia. So it's normal Jupiter-type planets, but with huge statistics. And you have a new satellite called the Nancy Grass Roman satellite, and it will try to detect gravitational lensing of small planets. And the potential of this technique could be to detect extremely small planets, but evidently it's a little bit frustrating because you have the effect of the gravitational lensing, but you cannot repeat the measurement. You cannot do comparable, new kind of measurements. But evidently, for statistical purpose, you can explore all this domain absolutely not covered by the present measurement. And in 1 year, I believe, Plateau satellite will be launched with measuring new kind of measurement on a lot of close stars, looking for the planets. You have spectroscopy of planet, Ariel, also will be launched in a few years, and so on. So you see, we are just at the beginning of the story. And I will finish here with some, I would say, more ambitious and projects on the long term. So what we would like to have the image of a Earth-type planet in the habitable zone and to do the chemical analysis of this object. At the present time, impossible. We do not have any tool for to do this. So the project proposed a few years ago by John Matter is to put in orbit in the sky a shadow, a star shade of something like 100 meters with some specific form for optical reason, and another satellite at maybe 170,000 kilometers is perfectly aligned to a distant star. So the net result will be to have the possibility to stop the luminosity of the star by this tool, and to have the possibility to see if a planet exists in the habitable zone, existing like the Earth, and to the image and the chemical analysis or the spectra of the atmosphere of this object. And so when detected by the Earth system, by the satellite system, it will be to complete the measurement using the ELT, the 39-meter telescope at the ground, to do the chemical analysis. So I will not see this project if decided. So it will not be before 10 years, 20, 40 years, I don't know. But you see, physically, it's possible to do this kind of measurement. The simulation of this kind of the physics, the optics of the system, you can see what is the contrast you can have between the star and a potential planet. It is something like 10 to the 10. So it's a very small planet could be detected in this distance directly by imagery. So, and this is only one example, but you have other projects like this. So I'm sure that in the coming, I don't know, 10, 20 years, we will have a lot of new possibilities to be proposed. And I have to thank you very much for your attention. Merci.
Thank you
Thank
so
you
very much, Dr. Michel. Saida.
No, go ahead.
No, it's you.
Thank you very much, Professor Michel.
Thank you,
for
Saida.
this excellent talk. and wonderful. It was a very rich learning journey for me, and I think for people who are all the people who participate. I think now we will have to answer some questions from our colleagues. But before I give the floor to my colleague to run the question session, I would like to mention why my colleagues from Al-Aqsa University were not here. I was just trying to contact them in the start of the talk, and finally they came back. One of them came back to me to inform me that while they were trying to go to an internet access, there was a bombing on them, and many of them are now in the hospital. One of them is in severe injury. The rest are fine, but they are in the hospital. So they asked me to send their greetings to all of you, and to keep praying for them and ask for your continuous solidarity. And this is why all of them were absent. I'm sorry to inform you about this,
Wow.
but this is what's going on now in Gaza. This is just one case. Yeah. Thank you.
Sad story.
Yeah.
Thank you, Saida. This is a terrible news. One of many in Gaza, as you say. Thank you for informing us of this. Arcadas, Pierre, and Senna, please, now we will go back to the scientific debate while our thoughts and love go to Gaza as always. Arcadas, Pierre, and Senna, the floor is yours.
Should I start?
Yes,
Yeah.
go ahead.
Yes.
Thank you for this wonderful talk. Maybe I don't know. One question I had was: do you think it would be possible to observe an event where a star actually swallows a planet, like orbit gets smaller and smaller, and would we be able to observe such a thing using Doppler spectroscopy?
What kind of object? Satellites?
No, the star, when a star swallows a planet, like the orbit of the planet gets smaller and smaller, and maybe eventually it falls into the star.
No. Because the time scale of the engulfment, because when you have the migration, you have the possibility sometimes to have some engulfment of planet, but the time scale is so short compared to the probability to observe this object. I don't know. I don't believe, no. But it's true that you have a lot of work made to analyze, because if you have the engulfment of a planet in the atmosphere, maybe you can have small change of the chemical composition of the stellar atmosphere, for showing that you have suffered from this kind of event. So you have people working for that, but you cannot observe directly the event.
Okay, thank you. And another question is, like, there used to be something kind of famous in the old times called Titius body law, like a law that Titius body law, like a law that gives numerical formula for the radius of the orbits of planets in the solar system, like a numerical formula. Do you know what I'm talking about?
No,
Titius body law?
I missed something. Please repeat the beginning.
So that there was this famous numerical observation called Titius body law.
Yes, okay.
So do you think like that's completely outdated now, or are there any updates to it, or is it completely wrong? Or I mean, looking at the current observations.
Yes, at the present time, I believe the interest of the body's law disappear quite a lot, because when you discover all the complexity of the interaction between this planetary system, we cannot understand from where is coming this law. But I can confess that the present situation is a paradise for people doing stellar dynamics, because when you have several planets, and you have a chain of resonance. You have several planetary systems with a chain of resonance. One planet is doing one turn, when another do two, another one 4, and so on and so on. So we have huge number of system with planet locked in the resonance, and this is it's a good type of information to say what are the mechanisms to form this kind of system. So you had a huge number of dynamicists studying this kind of situation. But the Bud law, I don't know.
Okay. Maybe one final question before I leave the floor. Do you think it would be possible to use Doppler spectroscopy for objects in the solar system, like maybe measuring their velocities to such a high degree that maybe we could observe some anomalies that we haven't been able to observe before? Things like that.
In the solar system?
Yeah.
Oh, personally, I'm a fan of, I dream of possibilities. As you probably know, that the satellites, space mission, have made the images of different satellites in the solar system, like Europa, Enceladus, and others. And this was quite a surprise, because Europa is covered by ice, but it's not a glacier, it's a ice field. So you have an ocean below this ice field. And due to the change of orbits, in fact, you have a lot of crack of the ice field, and some water is coming from below, from the ocean, and immediately when the water arrives in the surface, it froze and do some small excess of matter. And so if you have liquid water under the ice field, you can start to ask, do we believe that maybe unicellular form of life have been developed in this place? And at the present time, already one space mission was launched last year to measure few parameters of this kind of satellites. It's not doing the chemical analysis of ice, but in the future, I'm sure that some people or some satellite spacecraft will go and analyze some excess of ice coming from below and dream maybe to find some form of life. I don't know if we have what is the probability this will be a success, but if you can detect some form of life in this field, it will be huge impact, because you can analyze what could be the DNA of this form of life, and you have no way to exchange between the Earth and Europa. So if it is the same DNA or it's not the same, what it is the same amino acid, and so on. So, okay, I don't know, but I'm sure that you have a lot of space mission designed to go and analyze this thing. And more recently, you have another mission, because it was discovered that you have geysers in the atmosphere of Enceladus. Enceladus is a satellite orbiting Saturn. And so the space mission have a chance sometimes to go through the eruption of the geyser, pick some part of the molecules emitted, and start to analyze and to find. And recently they have announced some results. So it's not long-term fictions, it's working. So the existing the possibility of life inside the solar system are not completely closed. Maybe we have the possibility of huge step in the discoveries on Mars, evidently every year you have a lot of satellites, but also in the satellites of Saturn and Jupiter.
Thank you very much. Do you want to continue, Pierre or Senna?
Yes, I can take the follow-up. So maybe a few more general questions before I come back to the topic. Of course, astronomy is one of the oldest sciences. You mentioned at the beginning Greek astronomers. Do you think that the astronomy has changed a lot since then, or is it still fundamentally the same as we did thousands of years ago?
Okay. Yes, it's true that the interest for what you are looking in the sky exists from several, but today I believe it's the same interest. I remember that at the present time, the people are asking to have lectures, to have presentations for the public and so on. It's really, this domain corresponds to a huge question of people. And evidently, at the beginning, 2000 years ago, it was only philosophy, but now you have all the support of science. And and I'm myself completely overloaded by the request to have conference and lectures.
Maybe another general question. Are the two sky hemispheres known to the same degree, or do we know one better than the other today?
It depends on the distance where you are looking for. If you are looking at the scale of the galaxy, the southern sky is especially interesting because it's the location of the center of the galaxy. So all this fascinating place in the center of the galaxy where you have the black hole, you have a huge black hole in the center of our Milky Way with a mass of 3.7 million of Earth mass. And this was detected, I don't know, 20 years ago. It's absolutely fascinating. So you have this bias. If you look for the immediate distance, so it's 100 parsec, 100 light year, I don't know, of the sun, I believe all directions are equivalent. And if you do cosmology, if you are looking at very large distance, much bigger than the Milky Way, in principle, it's almost the same distance, the same interest in any direction.
Okay. One more question for me, one from the audience. Could you explain the relationship between the period and temperature of Jupiter-like planets? And a secondary question, do we have an idea how close these planets are to being stars themselves?
Yes, alors, the first one, 51 peg, is with a period of 4.2 days. I believe, if I remember correctly, it corresponds to 8 solar radii. So it's really close to the star. And being so close, evidently, the net result that the temperature is much, much higher. So, for example, the typical temperature of the atmosphere of 51 Pegasi is something like more than 1000 Kelvin. And so evidently, when you are extremely close to the star, it's extremely very hot. And for example, you have the situation of this rocky planet with orbit of a few hours, orbiting star a little bit more massive than the sun. In fact, this corresponds to a temperature sufficient to have the melting of silicates. So we can consider this object should be lava planet.
Okay, thank you. Sena, you have questions?
Yes, thank you. The first question I would like to ask from the audience is, in terms of decision making, what would be the next milestone you'll advise the governments to fund researching? And it's same for young researchers. And as a second question, would the chemistry of the planet's atmosphere be a good point, or is it too ambitious in the observable future?
Oh, sorry, I have to ask you to repeat the first question slowly.
Of course.
Yes,
in terms of
you speak too quickly, my sweet Senna.
sorry,
More old brain.
Voilà.
in terms
Just
of
speak more slowly.
yeah, of course. In terms of decision making, what would be the next milestone you will advise the governments and young researchers to keep going on to for research?
Okay, it depends on the countries. In some countries, the situation is not specifically good right now. No, I don't know what. Okay, you have this always in the domain of space. The go there. The number of years needed to bring a project from the first design proposal to the launch is terrific. Most of them is 20 years. And even at the present time, you have too many nice project proposal. And as I mentioned before, you have all the interest for the satellites or external part of the solar system. For me, it's fantastic. This is exploration of the satellite of Jupiter and Saturn. I hope this will be launched in a few decades. On the ground, you have the construction of this huge telescope, and evidently it will be used evidently for solar planetary exoplanets studies, but the hottest topic will be the deep universe. And you have, at the present time, you have a huge interest and bring by the new satellite or have a problem with Euclid. You have the Euclid satellite studying the deep universe, and is always to solve or to study these incredible questions that the general relativity gave a frame fantastic for the evolution of the universe, for the cosmology, but we are facing with two incredible big questions. One is the fact that the mass existing in the universe is much higher than what is observed, and we know that it is not baryonic matter. And this is certainly one huge. What is this missing mass? Dark matter. And the second question, as you certainly know, that the universe was discovered 20 years ago to have an expansion accelerated. What is the reason of this acceleration? And you have all this very strange situation. On one side, you have some observation working so well. It's absolutely fantastic with the prediction of the cosmology, but we have these two big questions. So this huge telescope that the James Webb or on the ground, the 39-meter telescope will have a fantastic role to play. But as probably you know, the gravitational wave is also a huge avenue, and with the project to enlarge the tools to detect gravitational waves and maybe in the space, and to have a much long distance, and to have the capability to detect much smaller events, resulting in waves. And at the present time, I don't know, probably you know better than me, but we already have something like 300 events detected by this existing instrument. And this collapse of of black holes, but also collapse of engulfment of neutron star and so on. Absolutely fantastic. Donc, okay, I don't know what are the priority after, everybody try to be convincing to get to be selected because you probably have too many good ideas.
Exactly. I think if I'm not wrong, the number of the events detected are even higher this year, this fourth observation run of the gravitational wave detectors.
Yes,
So, as you said,
recently they have announced 120 new objects. Yes.
Yes. Thank you. So another more specific question from the audience is, how significant is the recent discovery of dimethyl sulfide in the exoplanet Chi-2-18b? If you know.
I don't know. I'm not so specialist of chemical reaction to comment on that. I'm always a little bit, comment dire, but not skeptical, but I like very much to wait a little bit. You have so many announcements made on the last 20 years or so, always claiming we have discovered something like this, and after 2 years, nobody considers this subject. You have a famous asteroids discovered in Antarctica, RL, AL, something, and with some feature looking like cyanobacteria. But in fact, as people claim, oh, we have seen life on an asteroid of Mars coming from Mars, and it was completely wrong. It's not, and you have several projects like this, and okay, it's a way. But I have to, in the specific point you mentioned, I have to mention I'm not working in the domain, but okay, be a little bit patient.
Thank you. Maybe one other question from the audience is, what are the challenges of using Doppler spectroscopy to detect signs of life on rocky exoplanets, and how can studying their atmosphere help?
No, the Doppler spectroscopy will not play any significant role in this domain because, as I try to explain at the end of my talk, that maybe this kind of future mission will try to do imagery direct of planets in the habitable zone. Okay, it's true that the direct use of Doppler spectroscopy for very small planets is absolutely facing a difficulty. That the magnetic activity of stars induce change of the apparent velocity at least at the level of 1 meter per second. And for Earth-type planet, Earth twin, we need to have something like 10 times smaller. So the problem is to extract a signal embedded in a noise 10 times bigger. So you have a lot of people working on this question right now to try to detect the signal of rocky planet. For the transit, at the present time, the James Webb Telescope in the space do not have enough photons and sensibility to do what I describe, so the chemical analysis of real Earth twin. Because the atmosphere of Earth-type planet is so small that the change in the spectra when the planet is in front or behind the star is so small. So for probably this will be the next generation Comme ça. Voilà. Okay. So the Doppler in Geneva, we have a long series of development in the Doppler spectroscopy with a specific present instrument called Espresso. Okay, you have a small window. If you detect a transiting planet with a period of about 1 year, about around hosted by a solar-type star, so the transit gives the information what is the period. So then after, with Doppler spectroscopy, you can accumulate enough measurement so the possibility to detect the mass. So, okay, maybe you can dream some happy situation when the combination of both could help. But we still have probably one of the important points to keep in mind that always we are facing new unexpected observations. Okay, the first object with 4.2 days was not predicted. After we we have made some measurement where we have been able to detect the angle of the orbital plane of the planet in comparison to the axis of the star. You know, in the solar system, the ecliptic is almost perpendicular to the rotational axis of the sun. We start to do this kind of measurement for exoplanets. All the first object was okay. The orbital plane was perpendicular to the spin axis of the star. And suddenly we have discovered object with the orbital of the axis of the star is like this, and the orbit of the planet was. And worse, we have discovered some planet orbiting in the wrong sense. So and so, you know, always you have unexpected discoveries. So for example, some of my young colleagues have studied the transiting planet of a planet orbiting a little bit hotter star, and doing the analysis of the spectra, they have discovered that at some phases you have rain of iron. The temperature was so high, it was enough to have rain of iron. And then you have coagulation and so on. So, okay, I believe we have to be open to discoveries of new things.
Thank you so much. And my final question will be more general. As someone who has dedicated their life to science and physics, what do you think most helps a scientist keep their curiosity alive, even in difficult times when practical struggles or conflict can make it hard to focus on the fascination about the universe?
Yes, I think the curiosity will continue. I'm quite optimistic. In the past, already some people have been facing period where the government or the politics was not really in favor of science, but I believe curiosity will be, it's something more fundamental of humankind, and that it will continue. But okay, the situation, we have not to ignore the difficulty of situation. You are better than me to do critics and comments on this point.
Thank you so much. I think actually, Senna, your question